Measurement of the size of a planet or a star. If small d is the diameter of a planet, the angle subtended by it at any single point on the Earth is called angular diameter of the planet. Let alpha be the angle between the two directions when two diametrically opposite points of the planet are viewed through a telescope as shown in figure. As the distance capital D of the planet is large, assuming it has been already measured, we can calculate the diameter of the planet as alpha is equal to small d upon capital D. Therefore, small d is equal to alpha capital D. Measurement of very small distances. When we intend to measure the size of the atoms and molecules, the conventional apparatus like vernier caliper or screw gauge will not be useful. Therefore, we use electron microscope or tunneling electron microscope to measure the size of atoms.
Do you know? For measuring large distances, astronomers use the following units. 1 astronomical unit AU is equal to 1.496 multiplied by 10 raised to 11 meters. 1 light year is equal to 9.46 multiplied by 10 raised to 15 meters. 1 parsec PC is equal to 3.08 multiplied by 10 raised to 16 meters, which is approximately equal to 3.26 light years. A light year is the distance travelled by light in 1 year. The astronomical unit AU is the mean distance between the center of the Earth and the center of the Sun. A parsec PC is the distance from where 1 AU subtends an angle of 1 second of arc. R is equal to 1 AU upon 1 raised to 99 the whole raised to C, which is equal to 1.496 multiplied by 10 raised to 11 the whole upon 4.847 multiplied by 10 raised to minus 6, which is equal to 3.08 multiplied by 10 raised to 16 meters. Example 1.2. A star is 5.5 light years away from the Earth. How much parallax in arcsec will it subtend when viewed from two opposite points along the orbit of the Earth? Solution. Two opposite points A and B along the orbit of the Earth are 2 astronomical units apart. The angle subtended by at the position of the star is equal to AB L, distance of the star from the Earth, which is equal to 2 AU upon 5.5 light years is equal to 2 multiplied by 1.496 multiplied by 10 raised to 11 meters upon 5.5 multiplied by 9.46 multiplied by 10 raised to 15 meters, which is equal to 5.75 multiplied by 10 raised to minus 6 radians, which is equal to 5.75 multiplied by 10 raised to minus 6 multiplied by 57.297 multiplied by 60 multiplied by 60 arcsec, which is equal to 1.186 arcsec. Do you know? Small distances are measured in units of 1 Fermi is equal to 1 F is equal to 10 raised to minus 15 m in SI system. Thus, 1 F is 1 femtometer FM. 2 angstrom is equal to 1 A is equal to 10 raised to minus 10 meters. For measuring sizes using a microscope, we need to select the wavelength of light to be used in the microscope, such that it is smaller than the size of the object to be measured. Thus, visible light wavelength from 4000 angstrom to 7000 angstrom can measure sizes up to about 4000 angstrom. If we want to measure even smaller sizes, we need to use even smaller wavelength, and so the use of electron microscope is necessary. As you will study in the 12th standard, each material particle corresponds to a wave. The approximate wavelength of the electrons in an electron microscope is about 0.6 angstrom, so that one can measure atomic sizes approximately 1 angstrom using this microscope. Example 1.3. The moon is at a distance of 3.84 multiplied by 10 raised to 8 meters from the earth. If viewed from two diametrically opposite points on the earth, the angle subtended at the moon is 1 degree 54 minutes. What is the diameter of the earth? Solution: angle subtended theta is equal to 1 degree 54 minutes, which is equal to 114 minutes, which is equal to 114 multiplied by 2.91 multiplied by 10 raised to minus 4 radians, which is equal to 3.317 multiplied by 10 raised to minus 2 radians. Diameter of the earth is equal to theta multiplied by distance to the moon from the earth, which is equal to 3.317 multiplied by 10 raised to minus 2 multiplied by 3.84 multiplied by 10 raised to 8 meters, which is equal to 1.274 multiplied by 10 raised to 7 meters.
Measurement of mass. Since 1889, a kilogram was the mass of a shiny piece of platinum-iridium alloy kept in a special glass case at the International Bureau of Weights and Measures. This definition of mass has been modified on 20th May 2019. The reason being that the carefully kept platinum-iridium piece is seen to pick up microparticles of dirt and is also affected by the atmosphere, causing its mass to change. The new measure of kilogram is defined in terms of magnitude of electric current. We know that electric current can be used to make an electromagnet. An electromagnet attracts magnetic materials and is thus used in research and in industrial applications such as cranes to lift heavy pieces of iron or steel. Thus, the kilogram mass can be described in terms of the amount of current which has to be passed through an electromagnet so that it can pull down one side of an extremely sensitive balance to balance the other side, which holds one standard kg mass. While dealing with mass of atoms and molecules, kg is an inconvenient unit. Therefore, their mass is measured in atomic mass unit. It will be easy to compare mass of an atom in terms of mass of some standard atom which has been decided internationally to be C12 atom. The 1/12th mass of an unexcited atom of C12 is called atomic mass unit AMU. 1 AMU is equal to 1.6605402 into 10 raised to minus 27 kg with an uncertainty of 10 in the last two decimal places. Measurement of time. The SI unit of time is the second, written as S. For many years, duration of one mean solar day was considered as reference. A mean solar day is the average time interval from one noon to the next noon. Average duration of a day is taken as 24 hours. 1 hour is of 60 minutes and each minute is of 60 seconds. Thus, a mean solar day is equal to 24 hours is equal to 24 into 60 into 60, which equals 86,400 second. Accordingly, a second was defined as 1 upon 86,400 of a mean solar day. It was later observed that the length of a solar day varies gradually due to the gradual slowing down of the Earth's rotation. Hence, to get more standard and non-varying constant unit for measurement of time, a cesium atomic clock is used. It is based on periodic vibrations produced in cesium atom. In cesium atomic clock, a second is taken as the time needed for 9,192,631,770 vibrations of the radiation, that is wave, emitted during a transition between two hyperfine states of Cs-133 atom.
Do you know why is only carbon used and not any other element for defining atomic mass unit? Carbon-12, C⁻², is the most abundant isotope of carbon and the most stable one. Around 98% of the available carbon is C12 isotope. Earlier, oxygen and hydrogen were used as the standard atoms, but various isotopes of oxygen and hydrogen are present in higher proportion, and therefore it is more accurate to use C12.
Dimensions and dimensional analysis. As mentioned earlier, a derived physical quantity can be expressed in terms of some combination of 7 basic or fundamental quantities. For convenience, the basic quantities are represented by symbols as L for length, M for mass, T for time, K for temperature, I for current, C for luminous intensity, and mole for amount of mass. The dimensions of a physical quantity are the powers to which the concerned fundamental units must be raised in order to obtain the unit of the given physical quantity. When we represent any derived quantity with appropriate powers of symbols of the fundamental quantities, then such an expression is called dimensional formula. This dimensional formula is expressed by square bracket and no comma is written in between any of the symbols. Illustration. First, dimensional formula of velocity. Velocity is equal to displacement upon time. Dimensions of velocity is equal to dimensions of L upon dimensions of T is equal to L1 m0 t raised to minus 1. Second, dimensional formula of velocity gradient. Velocity gradient is equal to velocity upon distance. Dimensions of velocity gradient is equal to dimensions of Lt raised to minus 1 upon dimensions of L is equal to dimensions of L0 m0 t raised to minus 1. Third, dimensional formula for charge. Charge is equal to current into time. Dimensions of charge is equal to dimensions of I into dimensions of t is equal to dimensions of L0, m0, t1, I1.
Some common physical quantities, their SI units and dimensions. 1. Physical quantities, density. Formula ρ is equal to m upon v. SI unit, kilogram per cubic meter, kg upon m raised to 3. Dimensional formula L raised to minus 3, m raised to 1, t raised to 0. 2. Physical quantities, acceleration. Formula A is equal to v upon t. SI unit, meter per second square, m upon s square. Dimensional formula L raised to 1, m raised to 0, t raised to minus 2. 3. Physical quantities, momentum. Formula P is equal to mv. SI unit kilogram meter per second, kg m upon s. Dimensional formula L raised to 1 m raised to 1 t raised to minus 1. 4. Physical quantities, force. Formula F is equal to ma. SI unit kilogram meter per second square, kg m upon s square or Newton n. Dimensional formula L raised to 1 m raised to 1 t raised to minus 2. 5. Physical quantities, impulse. Formula J is equal to Ft. SI unit Newton second, ns. Dimensional formula L raised to 1 m raised to 1 t raised to minus 1. 6. Physical quantities, work. Formula W is equal to Fs. SI unit joule, J. Dimensional formula L raised to 2 m raised to 1 t raised to minus 2. 7. Physical quantities, kinetic energy. Formula Ke is equal to 1 upon 2 mv square. SI unit joule, J. Dimensional formula L raised to 2 m raised to 1 t raised to minus 2. 8. Physical quantities, pressure. Formula P is equal to F upon A. SI unit kilogram per meter second square. Dimensional formula L raised to minus 1 m raised to 1 t raised to minus 2.
Uses of dimensional analysis. First, to check the correctness of physical equations. In any equation relating different physical quantities, if the dimensions of all the terms on both the sides are the same, then that equation is said to be dimensionally correct. This is called the principle of homogeneity of dimensions. Consider the first equation of motion, v is equal to u plus at. Dimension of LHS is equal to dimension of v, that is equal to LT raised to minus 1. Dimension of RHS is equal to dimension of u is equal to LT raised to minus 1. Dimension of AT is equal to LT raised to minus 2 into dimension of T is equal to LT raised to minus 1. LT raised to minus 1 plus LT raised to minus 1. LHS is equal to RHS. As the dimensions of LHS and RHS are the same, the given equation is dimensionally correct. Second, to establish the relationship between related physical quantities. The period t of oscillation of a simple pendulum depends on length L and acceleration due to gravity g. Let us derive the relation between t, L, g. Suppose t is directly proportional to L raised to a and t is directly proportional to g raised to b, and t is directly proportional to L raised to a into g raised to b. T is equal to k L raised to a into g raised to b, where k is constant of proportionality and it is a dimensionless quantity, and a and b are rational numbers. Equating dimensions on both sides, dimensions of m raised to 0, L raised to 0, t raised to 1 is equal to k into dimensions of L raised to 1 raised to a into dimensions of L, t raised to minus 2 raised to b is equal to k into dimensions of L raised to a plus b into t raised to minus 2b. Dimensions of L raised to 0, t raised to 1 is equal to k into dimensions of L raised to A plus B T raised to minus 2B. Comparing the dimensions of the corresponding quantities on both the sides, we get A plus B is equal to 0. Therefore, A is equal to minus B. And minus 2B is equal to 1. Therefore, B is equal to minus 1 upon 2. Therefore, A is equal to minus B is equal to minus 1 upon 2. Therefore, A is equal to 1 upon 2. Therefore, T is equal to K into L raised to half into G raised to minus half. Therefore, T is equal to K under root L upon G. The value of K is determined experimentally and is found to be 2 pi. Therefore, T is equal to 2 pi under root L upon G. Third, to find the conversion factor between the units of the same physical quantity in two different systems of units. Let us use dimensional analysis to determine the conversion factor between joule, SI unit of work, and erg, CGS unit of work. Let 1 joule be equal to X erg. Dimensional formula for work is dimensions of M raised to 1, L raised to 2, T raised to minus 2. Substituting in the above equation, we can write dimensions of M1 raised to 1, L1 raised to 2, T1 raised to minus 2 is equal to X into dimensions of M2 raised to 1, L2 raised to 2, T2 raised to minus 2. X is equal to dimensions of M1 raised to 1, L1 raised to 2, T1 raised to minus 2 upon dimensions of M2 raised to 1, L2 raised to 2, T2 raised to minus 2. Or X is equal to M1 upon M2 raised to 1 into L1 upon L2 raised to 2 into T1 upon T2 raised to minus 2, where suffix 1 indicates SI units and 2 indicates CGS units. In SI units, L, M, T are expressed in meter, kilogram and second, and in CGS system, L, M, T are represented in centimeter, gram and second respectively. Therefore, X is equal to kilogram upon gram raised to 1 into meter upon centimeter raised to 2 into second upon second raised to minus 2. Or X is equal to 10 raised to 3 gram upon gram raised to 1 into 100 centimeter upon centimeter raised to 2 into 1 raised to minus 2. Therefore, X is equal to 10 raised to 3 into 10 raised to 4, which equals 10 raised to 7. Therefore, 1 joule is equal to 10 raised to 7 erg.
Example 1.4. A calorie is a unit of heat and it equals 4.2 joules, where 1 joule is equal to kilogram meter square per second square. A distant civilization employs a system of units in which the units of mass, length and time are alpha kilogram, beta meter and gamma seconds. Also, J dash is the unit of energy. What will be the magnitude of calorie in their units? Solution. Let us write the new units as A, B and C for mass, length and time respectively. We are given 1A is equal to alpha kilograms, 1B is equal to beta meter, 1 C is equal to gamma seconds. 1 calorie is equal to 4.2 joules, which is equal to 4.2 kilogram meter square per second square, which is equal to 4.2 multiplied by A upon alpha multiplied by B upon beta the whole square multiplied by C upon gamma raised to minus 2, which is equal to 4.2 gamma square upon alpha beta square multiplied by A B square multiplied by C raised to minus 2, which is equal to 4.2 gamma square upon alpha beta square multiplied by J dash. Thus, in the new units, 1 calorie is equal to 4.2 gamma square upon alpha beta square multiplied by J dash.
Subscribe to my channel. Click on bell icon to get notification about new video.